Hello everyone, my name is Lakshman Purve and this is Lab 4. A brief introduction. The overall purpose of this lab is to predict the behavior of circuits with resistors that are both in series and parallel. We analyze the behavior of ohmic resistors and capacitors in this lab as well. The fundamental principles that are used in this lab are as follows. The loop rule and the node rule. The loop rule says that as you traverse or travel around a circuit, the overall differences in the voltage or the potential difference ends up being zero. And the node rule is basically stemming from the conservation of charge, that a wire that stems into two will have the same amount of electrons flowing through it. The conservation of energy and Ohm's law, which states that voltage is I over R, where I is the current in amperes and R is the resistance in ohms. And this is how we calculate the sign of the voltage depending on the direction of travel or traversal of the circuit. We define the system as the circuit and the surroundings as everything else. The assumptions we make in this experiment are that the resistance in the ammeters and the wires are negligible. This is our experimental model for the first setup. We have two 1.5 volt batteries with two ammeters and two resistors in series, one being 47 and one being 100 ohms. Using Ohm's law, we calculate that I ends up being 0.02 amperes, and we predict that reversing the connections would make the current negative. The voltmeter shows 3 volts because there is no resistance, just taking off the potential difference, and the ammeter shows 0 because the circuit is open, so there's no way for the electrons to flow. And these are the values we derived calculating the potential differences across several points. We say that using Ohm's law, we derive I to be 0.06 amperes, and the overall resistance as 48 ohms for the 47 one and 101 for the 100 ohm, with the wires and ammeters being 0 essentially. As you can see, this is the graph of the potential difference across the several points. And here we go into the experimental model 2, which uses a 10 ohm bulb and a 20 ohm bulb and a 200 millifarad capacitor and a 9 volt battery. The 2 ohm battery and capacitor are held in series. We observe that the light is initially bright, but it's dimmed down before going out because the capacitor is charging up in the meantime. We also conclude that once it's charged up, the flow of electrons ends up being 0 amperes. We observe for the second part, once in the discharge process, that the bulb is bright, but it continues to dim again. This is when the capacitor is discharging and the current again goes to 0 amperes. The time for discharge for the 10 ohm was 10.4 seconds and for the 20 ohm was 18.2 seconds. We then further analyze and draft up a time-dependent model. After plotting the values for 20 seconds, across 20 seconds, these are the values we derive, and we plot them out to get a line of best fit with an equation being y equals negative 0.2034x plus 0.1491. When we use our formula and inverse the slope value, we get a RC value of 4.92, which is somewhat similar to the one we derived analytically, with that being resistance times the capacitance, with being 6. So they're somewhat similar. The source of error in this experiment could be the rounding we did while the calculations, and most importantly, the human error made while getting the time and the values during the discharge. So what if we were to do this lab in real life and use an actual ammeter instead of the ideal simulated ammeter? What's the difference about the real ammeter and how would it affect the circuits we hooked it up to? Because we're assuming an ideal environment, we really can't do that in reality because the ammeters would have internal resistance and the circuits and the current we calculate across the wires would be lower because of the resistance internally in the ammeters. What if we were doing this lab in real life and use a real battery to charge a real capacitor with no resistor in the circuit? How would the ideal model predict the capacitor time to fully charge? And would this happen in real life? The capacitor would become charged immediately because there is no resistor. But this would not happen in reality because wires also have internal resistance, thus making the overall charging time and process slower.